All right, welcome class to week 4 of Introduction to Antenna Basics. Thanks for coming back if you've been able to attend the previous classes, or welcome to the first class. If this is the first one that you can attend, I know people are signing up all the time. So this class, and it's going to be a shorter class this time, and then next class will be longer, so that they'll balance out overall. But this class will be an introduction to planar antenna design, like on a PCB, printed circuit board. So I wanted to start off with some quick housekeeping notes, like I usually do. A couple things first that I did not mention from the last class, where we talked about wire resonant antennas and then traveling wave wire antennas. I mentioned a few, like half-wave dipole, folded half-wave dipole, quarter-wave monopole. You can have multiples of, half and quarter wavelength antennas that will work. You will just have changes to your gain and radiation pattern. So the ones that I went over, I've been going over a very select few types of antennas. I've tried to concentrate on the most common that might be of most interest to the class. And I'm kind of guessing there, right? But for the dipole alone, you're going to have the infinitesimally small dipole, and then the very small dipole, like less than 1/10 of a wavelength, things like that, that are also taught in a traditional university antenna design class that I didn't quite go into. But I did want to mention those in particular, because I also wanted to mention antennas when you don't want them. And so this class is about how to design antennas that you want, right? But nowadays, it's almost just as important to know how to not design an antenna, right? Because particularly when you're doing printed circuit board design, or routing your traces, you don't want antennas in areas that you don't want to radiate. And so one example of this that I dealt with personally were alligator clips, just the real standard alligator clips that you might have in any lab bench. I was able to test one of my senior design receiver beacon projects by using an alligator clip as an antenna, right? So that can show you just how easy it is to have an antenna when you weren't maybe necessarily trying to have one, if you're not deliberately trying to use the wrong thing as an antenna like I did. But that's, particular importance when you're talking about things like dipoles. It's just a little extra trace here or there can end up radiating, if it's the right frequency. So I wanted to be sure to cover that. I know someone asked for a nano VNA measurement tutorial. I wasn't able to get to that before this class. I'll have it by the end of the class. I'm not sure yet if it will be just a PDF file with notes and kind of call outs, or if I'll be able to record a short video and actually be able to show on camera what I'm doing. If I can get good enough resolution that I think that'll be helpful, I'll include that as well, so that there'll be a pair. But since that's not quite antenna design, I wanted to do it a little separately for those that were interested. Another point I mentioned in a previous class about one open source antenna design simulator that I had found and have used just a little bit, and I'll include screenshots in today's lecture, is Sinos. And they've actually changed their licensing so that they now have a free community license for students. It's free for anyone for non-commercial use. And the link is here on this page. And I also wanted to mention, Hackaday didn't tell me to say this, but I just thought it was really cool and would be applicable to the demographic of the class. They have a hack chat next, I think it's Wednesday, June 2nd, on hobbyist satellite communication that looks really cool. I don't think that I'll be able to attend because I have a standing meeting at that time I might try to sneak out and see if I can attend. But if you have any interest, and particularly because the next class is going to go over more microwave frequency antennas and things like horns and reflector parabolic antennas that you would use for satellite communication, that would be applicable if you have any interest in that. So there's the link to that. So as an overall recap from last class, particularly if you are going to take the final quiz for certification, you should know that dipoles and monopoles, generally speaking, are low gain. They have an omnidirectional radiation pattern, and they're linearly polarized, and they're resonant antennas that resonate from the wire. And of course, you can combine different variations to get circular polarization, if you kind of array them together or have directional, but standing alone from just basic principles, that's how those antennas behave. And that's a good thing to know. Impedance for a half-wave dipole antenna in free space is about 73 ohms, which is about 1/4 the input impedance for a half-wave folded dipole antenna. I think memorization of numerical qualities is a stupid thing to be tested over. Maybe not stupid, useless thing to be tested over, but generally speaking, you should know that they are different, right? And it's also important to know that a balun converts between a balanced or differential signal, like going back and forth, like a half-wave dipole antenna, and an unbalanced signal, for example, on a coaxial line. And there are also unbalanced antennas and balanced signals, right? A balanced signal is a transmission line. So this is one example. Not all antennas are one way, and not all feed lines are another way, but you should generally know what a balun aims to do, right? So as I stated, this class is going to be a little bit shorter. I'm going to go over slot antennas, do a more extensive overview of patches, and particularly go over how you would circularly polarize a patch antenna, discuss a little bit about microstrip lines, particularly in the context of feeding a patch, right? And I said I was going to cover Vivaldis because I had a vague memory of designing a Vivaldi and didn't remember it being that difficult. And then looking into it to teach on them for the class, and I thought that they were a little bit more advanced than something I wanted to cover. So I'm going to give a very brief overview of them, but not go into depth. So let's get started with slots. And slots are one of my favorite kinds of antennas because they sort of make no sense to me. And I know a lot of other people have that same initial reaction, right? Because we think of an antenna as a piece of wire that radiates, right? And that would make sense. You apply a, alternating current, there's a voltage, and that creates a field. The field propagates, right? Because you have this piece of metal, and that's how that works. And a slot is nothing, right? It is the absence of it. And so it's a complement. It's not the same as a half-wave dipole, meaning that it is approximately half-wave, a long-laid slot cut in some conductive plate. Now, you might simulate this in simulators such as HFSS by simply constructing a perfectly electric conductor in an infinite plane, and you just cut a rectangle out of it, right? That would give you the best performance. Now, in real life, of course, we don't have infinite ground planes, right? But what determines the resonant frequency is the length of the slot. It should be approximately half-wave, and the width of the slot determines the bandwidth. And where on the slot you apply your feed point is how you do your impedance match. And one of the interesting things about these is that they are linearly polarized, but opposite to how you would think for a dipole. So if you have a dipole antenna, it's in a vertical position, it's going to be vertically polarized, right? But if you have this plane and you have a vertical slot cut into it, it's going to be horizontally polarized. So again, a complement to a half-wave dipole, not the same as a half-wave dipole. You also commonly see this in slotted waveguides. That's what a lot of the documentation shows. And I wanted to bring this up because they are so interesting. They're not as common. You'll see them in, aerospace industry, like radar applications are a lot of it. But I have seen some hands take an interest in playing around with them just because they are so unique. So I definitely did want to cover it. And it can be an interesting project, right? That you are making a slot radiate. You're simply, cutting a hole out of a sheet of metal, right? Which is it's an interesting concept to make as an antenna. And now I'm going to go over patches. So patches are extremely common for antennas. They're cheap generally, right? Cheap and easy-ish as antenna design can get. Although you can certainly make them more complicated with different varieties, and there's still ongoing research all the time about how to improve gain or bandwidth or polarization. And you use them a lot in antenna arrays. I won't be going into arrays, as I've stated several times in this class, but I will mention kind of how you would start to organize that feed network, right? So you can see a model of a patch antenna shown on the right. That's an S-band template of an inset microstrip patch from the CNOS software that I've been playing with, and I'll describe what an inset fed patch is specifically here in a couple slides. But typically these are square, that's the most common, right? But you can also have more rectangles, ellipses, kind of, fattened circles or circular patches, which I think are kind of also more common, particularly when you are getting into trying to fit patches, and particularly arrays of patches into smaller spaces. If you are constrained on your size, sometimes a circular patch will fit better in whatever your constrained area is than doing a bunch of squares, right? These are really nice and low profile. They're really popular for, spacecraft on the sides of rockets. You can make them conformal on a cylinder to do, say, student rocketry telemetry. They have a directional pattern, right? Because it doesn't radiate beneath the patch as much, even though you might have some effects there, but it's more like a balloon shape. And I'll show a three-dimensional depiction of the radiation pattern, I think on the next slide. These are, you often use them for the low gain antenna on a spacecraft, even though they're not, you can have maybe commonly 6, 7, 8 dBi of gain, which is not maybe necessarily low depending on your requirements. If you're actually working on spacecraft from a ways away, that can be pretty low, right? They are naturally linearly polarized along the width of the patch, and I will go over several ways to make it circularly polarized. If you are going to play around with patches, I always recommend trying a linear polarization first, just because it is simpler and you are adding steps of difficulty in nailing that circular polarization, right? And if you know, you're a student and your ultimate goal is to make something circularly polarized, try to nail down the basics of a linear patch first, try to get it to your frequency and your impedance matched and everything like that before adding that extra complexity. I mentioned there are different ways of feeding them. Commonly, you're going to have, you know, transmission line fed as what's shown in this photo here on the right, or it can be with a probe, right? Like that you would connect an SMA connector to it. There are other more advanced ways of feeding a patch, like aperture coupling, but I won't be going into those. And some of the drawbacks are that they are naturally a narrower bandwidth, right? So you're going to get that resonance at a point, right? It's not going to have that very wide response unless you are working to create a wide bandwidth patch. And they're not the most efficient antenna, but they are much lower cost than some other designs. So I've linked to a kind of starting, I've linked to several calculators and I'll explain each one. So the following here linked is just very common microstrip patch antenna calculator. And I want to point out one of the issues with this. So I talked about different methods of feeding a patch, and a patch antenna has different input impedance depending where on the patch you are. So if you're directly in the middle of the patch, that has a 0 input impedance. And if you are coming right into the side of the patch in the wrong place, it's going to have a very high input impedance. So you need to work around and figure out what is the best match. But the general process, without overloading with the equations that you go through when calculating the dimensions for a patch, is first you calculate the width, and the width really sets your input impedance, and that's based off the frequency that you want and your dielectric. So you're going to have your patch antenna over a dielectric over a ground plane, right? Those are your 3 basic elements there. And then you have to calculate, or the calculator will do it for you, your effective dielectric constant, right? And that's because you might have a dielectric that you want to use, but things like height, the dielectric constant of the dielectric itself, and the width of the patch antenna all affect that. And then you use that to calculate the effective length. And then we have a smidge factor, a delta L, that we add, that you're going to extend that effective length by, right? And then you get your actual length of the patch. So that's the process that a standard patch antenna calculator goes through. That's the process that you're shown when you learn antenna design based on the equations. And they're not overly difficult equations. There's no calculus involved. It's just square roots and everything and a lot of algebra. So it's not overwhelming. It's just that you have to go through several steps if you're going to do it by hand. But if you have an interest, by all means, feel free to go through the math by yourself and confirm that the calculator is correct in what it's spitting out. But generally what it's going to give you is a square that's approximately half wavelength by half wavelength, right? Not exactly, it's going to be modified by these effective length and length extension calculations, right? So what's it like when you want to design a patch in a simulator? So this is the Sino software that I mentioned before. I do like that this has a template for a patch antenna. with everything labeled. If you're working in something like HFSS, they might have, they typically have some examples that will come with the package, but otherwise you draw all this out, by yourself and subtract away the parts that you don't want. And it's a lot of, typically, if you're doing good simulation software design practices, you're using variables and inputting those variables yourself that you've calculated. But here, this software takes you through the substrate width, length, and height. Substrate height is usually pretty standard. This has rounded up to 1.6 millimeters. I think a standard PCB board is 1.57 off the top of my head. And how much bigger you want this to be than your patch can depend on how much space you have. And also some good rules of thumb recommend that it's at least 3 times your substrate height more than your actual patch, right? But that can also depend on what actual dielectric constant that you're using for your dielectric, because there are a variety and things like that. A good resource to consult if you're going to be getting a little creative with your dielectrics is to consult the data sheet. They will typically have that kind of information there for you. And there are different dielectrics across the market that are typically used for, say, patch antenna arrays or spacecraft patch antennas due to different properties. So it kind of depends on what you're looking for. Patch width and patch length. You can see that they're pretty close to being a square, but not quite, right? And feed width. So I'm going to talk about this a little later in the class when I talk about microstrip feed lines, but your feed width is what sets your impedance, right? Depending on your frequency. And this is an inset patch. Again, remember I said if you are trying to apply your source right there at the edge of the width of a patch with nothing else, that's a very high impedance. So an inset patch is a very common way of matching the impedance that you need, right? And it's particularly popular because it doesn't take up more room, right? And it's all in that one design. Again, there are others that are available, but that's a common one, and that's one that this software already has in its template. And this is what the radiation pattern looks like. Like I said, kind of like a balloon coming out of the antenna, right? And you can see the directivity here is about at its maximum point, which is, bore site, and of the patch is 7.3 dB. Remember, directivity does not take into account ohmic losses of your antenna, unlike gain does, right? So they're not a direct match with each other. And remember, we said patch antennas are linearly polarized along the width of the antenna. What does that mean? Well, you can see the lines here in the electric field illustration here on the right? So it's coming out linearly polarized, kind of horizontal-ish from the way that it looks on the screen. And I wanted to mention on the left, it's fairly directional compared to an omnidirectional antenna, right? But to make it more directional than that, to have a more directed beam, or to steer the beam, which is more advanced, that's when you get into having an array. That's what that gives you. If you're needing an antenna that is low profile and steerable or higher gain, that's when you're going to go into perhaps a phased array of patches instead of a singular patch. And one thing that I want to discuss is just kind of at a high level is the field behavior of a patch antenna. So you can see here you have your, half wavelength patch on top. You have your dielectric height for H, and you have your effective permittivity, which is a property of the dielectric that you're using. And this is kind of what the field behavior looks like, right? So if you get to work with a more advanced antenna design software, you can actually plot these fields to make sure that the field behavior is what you're expecting, right? And if you do have access to a software simulation tool that does have that capability, that is the number one thing that I would always recommend when you're first starting out with your designs, is look at the field behavior. Does it look like how you expect it to look? Because that's the first sign that you might have done something wrong, right? And that might be that you have designed it horribly, horribly wrong, which I have done, or B, that you might just have not done something correctly within the tool to get the correct simulation, which I've also done, right? But that can be one of the first clues, because fields in standard designs should always behave how they're supposed to behave, right? If you're getting into some new wild designs or doing active research, that's going to be a little less helpful. But for things like, microstrip or patches, they should behave just as they're shown from the basic physics. And one of the things that you might hear about is fringing fields, and that's going to be those lines that kind of come up like this, and you'll have effects from that in the antenna without going too deeply in it. But this is how the antenna actually radiates its radiation, its fields. So as I showed, that was kind of a basic standard linearly polarized design. I'll also cover, when discussing how you would feed a circularly polarized patch, they have some good examples that can also be applied to linear polarization. There are several methods that I'm going to discuss here of, varying difficulty, or some people might just have a personal preference. One that I don't have a photo for is listed at the bottom of the slide, dual feed, right? And that's a really standard way of feeding anything with circular polarization, right? Instead of just feeding it at one point, you feed it from two different points, right? To get that phase offset so that you can have that circular polarization. And remember, the circular polarization is when the electric field vector, kind of creates that circle as it's rotating. And you kind of have that perfect offset with the magnetic field vector as it rotates. And perfect circular polarization is that both of those have the same magnitude. If it's going to be off slightly, you're going to have a slightly elliptical polarization. And that ratio of the polarization is in circular polarization, it's called axial ratio. That's going to be a spec that you'll see on circularly polarized antennas. Either if you're purchasing them, you'll see it on the data sheet, or if you're buying them, that's something that you'll want to stipulate to your vendor, right? And that can depend on how much polarization mismatch loss you can tolerate in your system. And that's where that kind of comes from. So looking into different methods of feeding and applying circular polarization, the best photos that I could find were from my antenna theory book that I've discussed before. Polarized, that's very common. And so if you have almost a perfectly square patch, you can feed it straight from a corner, right? But you have to have a very nearly square patch And this kind of constrains where you can come in exactly, and you might be, constrained in your space. And that one is not as much of a popular application as I've seen. And next, you can have if you're doing a probe fed, like for example, with an SMA connector, you can feed it along the diagonal that's shown there on the bottom screen. And depending on which of your dimensions is longer or wider, feeding it along that diagonal, which side you're on is going to be either left-hand circular polarized or right-hand circular polarized. And remember, we said the middle point of a patch is 0 impedance. So you're not going to see a feed point directly in the middle of a patch antenna, right? Because we don't have a 0 ohm connector. Another method, and I've played around with this, I didn't prefer this method as much, is cutting a slot into your patch to force circular polarization, either right hand or left hand. And you have to kind of play with your dimensions a little bit if you're going to do this. I simply didn't like having to play with that many elements and keeping the, what am I trying to say, slot centered. It seemed like a lot of variables to manipulate at the same time to me. But by all means, if this is your preferred method, or if you have a lot of experience, this can definitely be a version of circular polarization to try. And one of the methods that I preferred more was the trim square method that's shown on the left. And you can feed it from, either 0.1 or 0.3 there, and then you just can trim your corners there to make circular polarization. And as I mentioned previously, you can also have circular patches or even elliptical patches, and you can add tabs on them to do circular polarization. That's not a method that I've personally done myself because I haven't made any elliptical patch antennas. But those are some of the methods if you're interested in trying that out. And I said that I would discuss microstrip lines. They're pretty straightforward. The biggest thing that you need to know, a transmission line or the microstrip line is just a transmission line for the RF that's separated from the ground plane by a dielectric, right? So it makes good sense to have that as your feed line to, say, a patch antenna that we just discussed. And your impedance of the line is primarily determined by your width. There's going to be some other factors in there, such as, your dielectric and height. But again, dielectric height can be pretty standard. So when you're trying to match your width is really what you're going to be playing around with to try to match that to whatever you're going for, let's say 50 ohms, right? And so the wider the strip, the lower the characteristic impedance. And this should make sense if we think about it from a pipeline perspective, right? If you have a very small diameter pipeline and you're trying to force a large amount of water through, you're going to have a lot of pressure, right? But if you have a much larger diameter pipeline and you are pushing the same amount of water, or say current, through, it's going to be much lower pressure, much lower resistance, much lower impedance, right? So that should be intuitive that the wider your strip is, the lower your impedance is, so that if you're doing your calculations, if you're running your simulations, which way you need to go, right, to play with it and make it correct. And I'm going to double back. Where do I want to go? I'm going to look at this slide because I didn't make a slide for it, but I do want to go over it. Let's say you want to match to this line that is 50 ohms, but you have some other transmission line offset from your antenna that is not 50 ohms. How do you do the match between that? And one thing that I didn't put in my slides and that I probably should have is a quarter wave transform match that you'll see. And that is kind of what it sounds like, is when you add in a quarter wavelength of transmission line between the 2 points that you're trying to match, right? And so that's another application of when you're going to need to have your microstrip line impedance matched, and when you might want a calculator to make sure that that's correct as well. And I am going to very briefly touch on Vivaldis. This was one of the few open source images that I could show. You can see it's got the very plain dielectric. I remember them being easier when I was playing around and designing them for fun. But I didn't actually have to send one to a board house, so maybe that was why I thought they were fun. But Vivaldis are a good way to have a very directional pattern on a PCB without doing an array, right? And you typically see these at higher microwave frequencies. I think there are several versions available, just commercial off the shelf, for working with Wi-Fi and Bluetooth frequencies that I've seen that are pretty cheap. They are linearly polarized, again, a directional pattern, so that means that they have high gain, right? And when we talk about patterns and gain, they're highly correlated, right? They're proportional to each other, because gain and patterns are kind of like having a really squishy balloon. It goes where you push it, right? You start off with a perfect sphere from that isotropic antenna that we talked about that doesn't really exist, right? And then you form your pattern, and that's where your gain goes, right? So omnidirectionals are going to have lower gain because they're more spread out, right? And then directionals are going to have higher gain because you're really pushing that pattern into that shape, right? Just think of it as molding this sphere of radiation pattern from a perfect sphere of an isotropic antenna where you have a very set amount of gain that's available, right? You're shaping it. And that's why your gain and your pattern are always highly correlated, right? So one of the things that Vivaldis are really liked for is that they naturally have a much wider bandwidth, unlike those patch antennas that we talked about that have a very narrow resonant frequency bandwidth. However, you're probably going to need a balun depending on what you feed your Vivaldi with. There are also kind of three-dimensional egg crate array versions that are publicly available on the internet that you can see that I'm less familiar with. You can see this one is fed with a little piece of line there and a SMA connector across. You can also do One of the kinds of antennas that I didn't talk about that is commonly taught for PCB is inverted planar F antenna. It looks like an F, right? And it has sort of a similar feed methodology to it. And one of the other antennas, well, I'm going to talk about that on the next slide. But Vivaldis are an option if you're looking for much higher gain, a directional pattern, and particularly if you need a wider bandwidth, but they are harder to match, or maybe not harder, they might take a few more steps to match than a simple patch, right? So one of the things that I wanted to mention on tips and tricks for these planar antennas, and one of the things that I've deliberately not covered is the kind of PCB board antennas that you will see on RF circuit boards, right? And most commonly, those are going to be, quarter wave traces above a ground plane, right? I'm less familiar with RF circuit board design. I have a link to, I think, a good overview of someone in the resources section, but stuff that you'll see, especially for playing around hobbyist use of Bluetooth and Wi-Fi boards and modules. I personally am less familiar with that. I should not be teaching a class over that, but some of this does apply, and so that's why I kind of wanted to mention it here on tips and tricks. So one thing that I have personally seen firsthand is the higher the frequency, well, first of all, the higher the frequency, the more difficult kind of everything gets, right? Because the higher your frequency, remember that's inversely proportionate to your wavelength size, right? So the higher the frequency, the smaller your wavelength gets. And there are different effects for every kind of wavelength, right? Particularly if we're talking about all kinds of situations like ionospheric effects, those affect long wavelengths differently than they do short wavelengths. But if you think about a wavelength, and I'll just use a piece of coax here as an example. If I have this piece of coax, and let's say I have a defect or something that's going to affect it that's, an inch long or, 2.5 centimeters long, that's not much in proportion maybe of this wavelength. But when your wavelength gets much smaller and smaller and smaller, it doesn't have to be much to have an effect, right? Because it's taking up a proportion of that wavelength, right? And microwaves can be difficult to work with sometimes because, humans are all generally the same size, and we're trying to work with tinier and tinier wavelengths. And things like surface roughness start to affect your design. Things like, here's one example that I'll talk about more in depth in the next class. This is a 3D printed horn antenna for X-band, approximately 10 to 12 gigahertz. And this has conductive tape on it, right? So at lower frequencies, the edges from those pieces of tape overlapping aren't going to be as big a deal as if you go into much higher frequencies, right? And you start getting a lot of diffraction at the higher frequency range that you go. And so that's something that can make it a little bit more difficult to work with, right? And that's something to keep in mind if you're going to be working in those frequencies, and particularly if you're kind of playing around and using rougher methods to construct your antennas versus having them sent off professionally to a board shop, or if you're doing it professionally, right? But even doing it professionally, surface roughness, in those kind of microwave ranges still might affect your design in real life if you're not factoring it into your simulation by, you know, maybe a couple tenths of a dB, right? And if you have very, very strict requirements, that might be something that you should consider, right? As I mentioned, your board dielectric should be suitable for your application or your environment, right? You're not going to have the same dielectric kind of goofing off at the house as something that you would send on a spacecraft around Jupiter, where you're having to worry about atomic oxygen requirements and radiation environments, things like that, right? So check the data sheet, which is kind of a common mantra for anything in hobbyist, RF and electronics, etc. At least check the data sheet and then determine how you want to break it if you're that kind of person, right? If you're doing an integrated board, which, as I said, is something that I'm less familiar with, you do want to use higher quality FR4 circuit boards. I do know that as much. And you also want to be careful if you're integrating a board onto your antenna. Remember, we talked about fields and field distances. You don't want to be putting other components super close to your antenna, particularly in that near field distance. So, you know, do the calculation for the near field, make sure you're not putting anything important in there. And finally, don't forget your connector footprints, right? If you design a beautiful patch antenna and you send it off to the board house and it comes back, and then you realize, oh, I forgot my SMA connector footprint, you're going to have to redo it, right? If that's you know, your chosen method of connector. Obviously, it differs depending on what you change for your design, but don't forget it. And double check your measurements for your connector footprints on your boards and make sure that they match. Really, always double check your footprints for any PCB, right? I had a professor who always taught that you can print them out and actually put, if you're doing, you know, through hole or even SMA, print it out and put components on top of it, you know, to double check, particularly if it's your first design. If you're an old hat at that, then you probably know way more than me. So some of the resources, there was a good article, I think it's antennatheory.com, on microstrip patch antennas that kind of shows the math. It talks more about those fringing fields. I have a couple of calculators, one that I showed the microstrip patch antenna calculator, and another one that specifically covers that inset fed microstrip patch antenna and that has available tools. I think there are some MATLAB files that are available. The microstrip impedance calculator. If you also have access to simulation tools, sometimes you'll have microstrip impedance calculators within the tool. I know Microwave Office, you know, had that. So it was just something quick that you could do within the software that you're already using. I included a write-up of the slot antenna that I like. There's really not that many references on slots. But that's one of the ones that I learned from. If you're more interested in actually making a Vivaldis antenna, I included a write-up that I thought was good that went into particularly the feeding of, say, a microwave Vivaldis antenna that might be helpful. And the video that I talked about that, you know, was helpful to me about RF circuit board design by Michael Osman. And he kind of goes over just some of the basics of what might be helpful to keep in mind if you are going to be doing things like those, you know, PCB trace antennas, particularly for things like, you know, Wi-Fi or Bluetooth modules. Definitely good things about, you know, keeping your power separated from your RF traces, keeping your RF on the top of your board, and, you know, impedance matching, everything to 50 ohms, because that's impedance matching is always rule number one in RF. And with that, coming up next class, I'll be doing an introduction to more specific antennas for microwave. antenna design, and some of the topics I'll go over horns pretty in depth because they happen to be one of my favorite kinds of antennas, just because I've gotten to play around with them and have 3D printed them. I'll go over some reflector antennas, the dishes that you see for satellite communication or internet, things like that. Waveguides, I'll be going into not extensively into like modes or anything like that. I will be going into like cutoff frequencies and stuff like that for waveguides. Waveguide is both an antenna and not an antenna, right? If you have an open waveguide, you have an antenna. And that's actually what a horn antenna is, right? A horn is just an open waveguide that's been flared for gain. And if you don't understand that, we'll talk about that more next class. But just things that are more specific to those higher frequencies, and some additional tips and tricks for that. So with that, thank you so much, and I'll see you for our last class next week.